Hello everyone, today we have the pleasure to present to you our summary on turbo machines. Our group is composed of Talal, Julio, Kelly, and I, Stella. First, let's start with the definition of a turbo machine. A turbo machine is a mechanical device that consists of several blades attached to a rotor. It transferred energy between a rotor and a fluid. That transferred energy can be added to or extracted from a fluid. A turbo machine has two classifications, a pump and a turbine. For the purpose of our presentation, we'll be focusing to depth on turbine. So how does a turbine work? Essentially, a turbine extracts energy from a fluid. As you can see the figure above, the fluid exerts torque on the rotor in the direction of its rotation and produces shaft work. There is different type of turbines, such as impulse turbines and reaction turbines. That classification, it is based on how the fluid interact with the turbine's blades. For an impulse turbine, the pressure of the fluid doesn't change in the turbine itself. Instead, the pressure changes occur only in a fixed nozzle. Impulse turbine has 0 degree of reaction. Degree of reaction, by definition, is a change in enthalpy over the total energy change. As it's shown in the figures here, example of impulse turbines are Pelton turbines, turbo turbines, and cross-flow turbines. For a reaction turbine, the pressure of the fluid changes as it moves through the blades of the turbine. The pressure drop occurs in both a fixed nozzle and the moving vane. The degree of reaction in a reaction turbine is in between 0.1 and 0.7. Example of reaction turbines are Kaplan turbines and Francis turbines.
There are different types of flow that can take place in a turbine, such as axial flow, radial flow, and mixed flow. For the axial flow, the fluid flows through the turbine parallel to the axis of rotation, for example, the Kaplan turbine, as you can see in this picture. Another type is the radial flow, where the turbine discharges the fluid perpendicular to the axis of rotation. Finally, we have the mixed flow. In this type, we have a combination of axial and radial pumping action. The fluid flows radially and exits axially. How is this related to previous chapters? Conservation of momentum applies in steady flow situations, which is essential to the Navier-Stokes equations. We can consider the Navier-Stokes equations by looking at the way that the fluid flows into and out of the turbine. Like always, pressure, density, and temperature will impact the fluid, so it continues to apply here. Bernoulli's principle also applies here, relating pressure, height, and the velocity of a fluid at one point along its flow.
In this presentation, we have talked about the turbines in theory, but what about their applications in real life? So, let us start with the steam turbine, the single most utilized energy-producing method in the world. In a steam turbine, chemical energy is converted into thermal energy, either by combusting fossil fuels or by harnessing the heat generated from the decomposition of radioactive minerals. This energy is used in steam boilers, which produce high-pressure steam from the water pumped into them. Finally, the steam is expanded against the steam turbines, whose blade shape contribute to create a pressure difference between their two faces, resulting in the turbine's rotation. This movement leads to the shaft work on the attached generator, ultimately producing electricity. Although they follow the same principle as the steam turbine, the turbines used in hydroelectric power plants have a unique design, named Pelton wheels. These turbines consist of a circular disc, also known as runner, with several metal balls along its circumference. The water from the reservoir flows into a nozzle used for flow regulation. From the nozzle comes a jet of water, which causes the movement of the turbine, resulting in the production of electricity from its shaft work.
What about tidal turbines? Wind turbines and tidal turbines are very similar, with the only major differences being the fluid used to produce shaft work, how sturdy the machine must be, and the location of the turbine. Tidal turbines sit on the sea floor and run on the work from the tidal movement, which is produced by the gravitational pull of the moon and the sun along with the rotation of the earth. Tidal turbines can produce a lot of energy, even more than a wind turbine using the same size blade. This is because the density of the ocean is much greater than the density of air, which increases the energy output. The density of the fluid that goes through the turbine is directly proportional to the pressure applied to it, and therefore the energy produced by it. The denser the fluid, the more pressure is applied on the rotors, leading to a higher power output. This power produced can then be stored and used for electricity. Therefore, today you learned about how a turbine works, the 3 different types of flow in a turbine, and heard some real-life examples of turbines in action. If you want to learn more, you can check out our references here. Thanks for watching.